You think you know what it means to look inside an atom. You imagine a smaller camera, a finer microscope, more magnification, more detail. You picture a tiny solar system, a nucleus in the center, electrons somewhere around it, and you assume that if you could just zoom in far enough, you'd finally see what's really there. This is wrong, not a little outdated, not missing a few details, wrong in a way that makes the entire question suspicious, because inside is already a trap. Look is a trap too. You imagine the atom as a thing that has parts arranged in space, waiting for you to inspect them, like opening a watch and seeing gears, like cutting open a fruit and seeing seeds. You think the atom is hiding its structure behind a curtain, and measurement is just pulling the curtain back. No. When you look inside an atom, you don't reveal a picture. You force a decision. You don't discover where something was. You create where it is allowed to be. You don't passively observe. You collide with the very meaning of the word is. And the more carefully you try to look, the more violent the act becomes. The more you insist on clarity, the more the atom refuses to remain an atom. You've been trained to believe there is a final, crisp image at the bottom of nature, a last layer of reality where things sit still and have properties the way objects do. That belief feels reasonable. It feels earned. It's still wrong. Feynman's point wasn't that atoms are complicated. His point was that your instinct for what it means to understand is what fails first. You think inside means smaller. You think understanding works like a zoom lens. The closer you get, the more real things become. Blur turns into shape. Shape turns into structure. Structure turns into parts. And eventually, if you zoom far enough, you imagine you'll hit bedrock, the smallest pieces, the true furniture of reality. This instinct feels harmless. It works almost everywhere in your life. You cut open a machine, and inside are gears. You open a phone, and inside are chips. You split a rock, and inside are crystals. Each time, the same logic holds. Smaller pieces, arranged in space, doing the same kinds of things as the larger object, just tighter, faster, more hidden. So when someone says inside an atom, you don't hesitate. You imagine a tinier version of what you already know. Smaller parts, shorter distances, a clearer picture, waiting patiently for better tools. This is wrong, not because atoms are complicated, but because inside quietly assumes something that stops being true. Inside assumes there is a place to go. It assumes the atom is a container, that it has an interior the way a box does. That reality is built like nested shells, each one holding the next. And that knowledge is just a matter of peeling layers away. That assumption breaks long before you reach the atom. Try this instead. Imagine zooming in on a shadow. At first, the shadow looks soft, vague edges. But you assume that with enough magnification, you'll see its structure. Maybe tiny fragments of darkness, maybe grain, maybe something holding it together. You zoom in further, nothing sharp appears, no pieces reveal themselves. The shadow doesn't resolve into smaller shadows. It simply stops being the kind of thing that can be examined this way. Not because your tools failed, because your question was malformed. A shadow doesn't have an inside. Neither does an atom, not in the way you mean. When physicists say inside, they're already speaking loosely. They're borrowing a spatial word to gesture at something that is not spatial in the everyday sense. Something that does not sit there waiting to be uncovered. You don't find smaller objects arranged neatly in space. You find constraints, relationships, rules about what can and cannot happen. And here's the uncomfortable part. The moment you insist on looking more closely, the thing you're trying to look at stops being the thing you thought it was. The atom does not contain a hidden picture. It contains limits on pictures. You can zoom in forever on a photograph and eventually see pixels. But if you zoom in on an equation, you don't find smaller equations inside it. You find that inside was never the right concept to begin with. Atoms are closer to equations than to machines. They don't have parts arranged in space in the way your intuition expects. They have behaviors that only make sense when you stop asking where things are and start asking what is allowed. And this is where the discomfort starts. Because if inside doesn't mean smaller, then looking doesn't mean revealing. And understanding doesn't mean seeing. And the deeper you go, the less the language of objects helps you at all. Why looking is not passive? You treat looking as harmless. You imagine observation as a light touch, a glance, a neutral act that leaves the world exactly as it was before you arrived. You assume the universe doesn't notice that you're paying attention. That assumption works because, at human scales, it's almost true. You can look at a chair without denting it. You can measure the length of a table without shortening it. You can check the time without bending it. The act of observation feels separate from the thing observed, so you carry that instinct with you when you think about atoms. You imagine a better microscope, a finer probe, a gentler way of peeking. You assume the atom already has properties, and measurement simply uncovers them, the way dusting off an old inscription reveals letters that were always there. This is wrong. At the atomic scale, there is no such thing as a gentle look. To see something, you must interact with it, not metaphorically, physically. You must exchange energy. You must disturb it. There is no alternative method hiding in better technology. Imagine trying to measure the pressure of a balloon by poking it with a needle. You can choose a thinner needle. You can poke more carefully. But at some point, the act of measuring becomes inseparable from the act of changing the system. Atoms live permanently at that point. To locate an electron, you need something with a very short wavelength. Short wavelengths mean high energy. High energy means a violent interaction. The more precisely you try to look, the harder you hit. This is not a technical problem. It is not a matter of clumsy tools. It is a rule built into how information works. And here is where intuition really starts to fail. You think the disturbance is an unfortunate side effect, as if the electron had a precise position all along and you simply knocked it out of place while trying to observe it. That story is comforting. It's also false, because when you try to imagine the electron having a definite position before you look, every experiment rebels. Interference patterns appear where they shouldn't. Outcomes refuse to line up with hidden trajectories. Predictions only work if you abandon the idea that measurement reveals a pre-existing fact. Looking does not uncover a property. Looking creates a specific outcome from a range of allowed ones. Before the measurement, the theory does not assign the electron a location you simply haven't discovered yet. It assigns a set of possibilities, each weighted, none privileged. The moment you measure, one of those possibilities becomes real. Not because it was waiting, but because the interaction forces a choice. This is deeply unsettling because it reverses the usual direction of explanation. Instead of reality causing measurements, measurements help define reality. You are not a passive witness. You are part of the event. Your apparatus is not a window, it's a participant. The boundary between system and observer is not sharp. It's something you impose for convenience. And physics punishes you the moment you forget that. This is why asking, "What was the electron doing before we looked?" often leads nowhere. The theory does not contain an answer because the question assumes a kind of existence that is not available at that scale. The atom does not sit there patiently, fully formed, waiting to be inspected. It waits only in the sense that a rule waits to be applied. The atom refuses to hold still. You assume that if something exists, it must have properties. A location, a speed, a direction, something you could, in principle, write down. Even if you don't know the values, you believe they're there, hidden but real. This belief is so deeply wired that it barely feels like a belief at all. It feels like common sense. If a car is on the road, it's somewhere. If a ball is moving, it has a speed. If an object exists, it must be doing something. So when you think about an electron in an atom, you instinctively imagine it as incomplete information. You think the problem is ignorance, that we just don't know enough yet. This is wrong. The atom does not refuse to give you answers because it's secretive. It refuses because the answers you're asking for do not exist simultaneously. This is not about technological limits. It's not about noisy data or sloppy experiments. It's about the structure of the theory itself. You cannot assign the electron a precise position and a precise momentum at the same time, not even in principle, not even if you had perfect instruments, not even if the universe cooperated. The more sharply you define where it is, the less meaning the idea of how fast it's moving retains. And the more sharply you define how it's moving, the less meaningful the idea of where it is becomes. This isn't a practical inconvenience. It's a rule. The mistake is thinking of uncertainty as missing information, as though the electron has both properties and nature is just refusing to tell you. But the math doesn't describe hidden values. It describes incompatible questions. Position and momentum are not two blurry facts about the same underlying thing. They are two different ways of interrogating a system, and the system cannot answer both at once. This is where the object metaphor collapses. An electron is not a tiny bead carrying a list of attributes. It's closer to a verb than a noun. Something defined by how it can change, not by what it statically is. Try to freeze it into a snapshot, and the rules push back. Imagine trying to photograph a melody. You can capture its pitch, but then time disappears. You can capture its duration, but then the exact note dissolves. The melody is not hiding a single perfect frame. Its existence is spread across mutually exclusive descriptions. The electron behaves the same way. When you ask, "Where is it?" you force one kind of answer. When you ask, "How is it moving?" you force another. But there is no master description underneath that contains both. This is why the atom feels unstable to your intuition. You're trying to treat something that is fundamentally relational as if it were a thing with internal parts. You're demanding stillness from something whose identity depends on not being still. And the deeper you push, the clearer it becomes. The atom is not built from properties. It is built from limits on properties. There is no picture waiting for you. At this point, you start searching for a picture. If words fail, maybe images will help. Diagrams, clouds, shapes, something you can hold in your mind and rotate, something that feels like an object. Textbooks happily provide them. Fuzzy blobs around a nucleus, dumbbells, donuts, lobes stacked in symmetric patterns. The implication is subtle but powerful. This is what the electron looks like. This is wrong. Those images are not photographs. They are not snapshots of anything sitting in space. They are bookkeeping devices, visual translations of a mathematical object that does not live where your intuition expects it to live. You are mistaking a map for terrain. The wave function is not a physical wave sloshing around the atom. It does not ripple through space like water. It does not pile up in corners or thin out at the edges. It is a mathematical function that assigns a number to every possible configuration you could ask about. Those orbital pictures are contours of probability. They tell you where an interaction is more likely to occur if you perform a measurement. They do not tell you where something is. This distinction matters because once you cross it, visualization stops helping and starts lying. Think of a weather forecast. A map shows a dark region labeled 80% chance of rain. That shading is not rain hovering in the sky. It's not moisture smeared over the city. It's information about possible outcomes, encoded visually so your brain can digest it. Electron orbitals are the same kind of thing. They are forecasts, not clouds. And just like a weather map, they tempt you into imagining substance where there is only structure. You want to say the electron is in the orbital, that it occupies the shape, that it fills the region. But that language sneaks the object metaphor back in through the side door. The theory never says that. It says, if you look here repeatedly, you'll get hits with this frequency. Nothing more, nothing less. The wave function does not describe what exists in space. It describes how the world responds to questions. It lives in an abstract space of possibilities, not in the 3 dimensions your eyes evolved to navigate. This is why every attempt to draw the atom feels unsatisfying. No picture survives interrogation, because pictures assume the thing being pictured exists in the same space as the picture. But the wave function is not in space the way a chair is. Space is something it talks about, not something it inhabits. When you insist on a picture, you are demanding the wrong currency. You are asking for an image of a rule. And rules don't have silhouettes. This is the point where many people quietly retreat. They accept the equations, memorize the diagrams, and stop asking what any of it means. The discomfort becomes background noise. But if you keep going, something stranger emerges. It's not just that there is no picture. It's that the universe doesn't seem to need one. You are trained to expect motion. If something changes, you imagine it moving through intermediate states. If something happens, you assume there is a story connecting before to after, a cause that pushes, a mechanism that unfolds, a sequence you could slow down and watch. This expectation is so ingrained that it feels synonymous with explanation. But inside the atom, explanation stops working that way. An electron in an atom does not slide from one state to another. It does not climb a ladder rung by rung. It does not pass through the space in between. It changes outcomes. One moment, the atom responds to measurements as if the electron has one energy. The next moment, it responds as if the electron has another. There is no experimentally accessible during, no detectable intermediate configuration, no movie you could play in slow motion. This is wrong, your intuition says, because things don't just switch, they transition. But the atom does. The equations describe allowed states and the probabilities of jumping between them. They do not describe a microscopic journey from here to there. The theory doesn't hide the mechanism from you. It simply never includes one. And yet the predictions are precise. Spectral lines appear at exact frequencies. Transitions happen reliably. The math works every time. What's missing is not accuracy. What's missing is a cause you can picture. Imagine a light switch. You don't see electrons flowing through the plastic toggle. You don't watch the circuit reconfigure itself. You only observe outcomes, on or off. The explanation lives in an abstract description of allowed states and constraints, not in a visible transformation. Now remove even the switch. In the atom, there is no moving part you can point to and say, that's what changed. There is only a rule that says, this outcome is allowed now, and that one is not. When an atom emits a photon, the energy difference is exact, not approximate, not smeared, exact. The atom behaves as though it had always obeyed those discrete options and simply chose a different one. But choice is the wrong word. It suggests agency, deliberation, process. There is only compliance. The atom does not explain itself. It enforces itself. This is where classical causality quietly breaks. You expect causes to be local and continuous. You expect effects to grow out of prior states the way branches grow from trunks. But quantum systems don't always offer that narrative. They offer correlations between preparations and outcomes, stitched together by rules rather than mechanisms. This doesn't mean causality disappears. It means it changes shape. Cause becomes constraint. Explanation becomes permission. The question, how did it get from here to there, stops making sense, because here and there are not connected by a path. They are connected by a rule book. And the universe seems perfectly content with that. It delivers outcomes with ruthless consistency while refusing to tell you a story you can visualize. At this scale, knowing what will happen does not require knowing how it happens in the way your intuition demands. The atom doesn't run on gears. It runs on allowances. You imagine solidity as contact. You picture atoms as tiny hard things, pressing against each other, forming larger hard things. When you push on a table, you imagine resistance coming from little objects refusing to be displaced. This picture feels obvious. It's also wrong. At the scale of atoms, almost nothing touches. There are no rigid surfaces meeting, no microscopic bricks stacked into macroscopic walls. What you feel as solidity comes from what is not allowed to happen. Electrons are not permitted to pile into the same state, not because they repel like magnets, but because the rules forbid it. The system simply has no solution where two identical electrons occupy the same complete set of properties. This is not a force in the usual sense. It's a prohibition. Think about traffic. A traffic jam doesn't require cars to be glued together. It emerges from constraints, rules about spacing, rules about speed, rules about where a car is allowed to be next. The jam exists even though nothing is physically binding the vehicles into a solid block. Matter works the same way. The structure of atoms, the layering of electrons, the stability of molecules, all of it comes from restrictions on possible arrangements, from quantum states that cannot be shared, from configurations that are simply illegal. When you press your hand against a table, the resistance you feel is not atoms bumping into each other like billiard balls. It's the electromagnetic field responding to an attempt to overlap electron configurations that cannot overlap. It's the refusal of the system to enter forbidden states. No touching is required, only compliance with rules. This is deeply counterintuitive because it inverts how you think structure should arise. You expect substance to come first and rules to describe how it behaves. But here, the rules come first. The substance is secondary. Matter is not held together by glue. It is held together by grammar. And just like grammar, the rules are invisible until you try to violate them. You don't notice them while reading a sentence, only when something sounds wrong, only when a construction is impossible. Atoms behave correctly not because something is pushing them into place, but because alternatives are disallowed. Remove those prohibitions, and matter collapses into sameness. No structure, no chemistry, no differentiation, no solidity. What feels firm is actually rigid absence, a space of possibilities with walls you can't cross. And those walls are not made of matter. They are made of rules. What Feynman was actually warning you about. By now, something should feel unstable. Not the atom, your expectations. You were taught quietly, implicitly, that understanding means seeing. That explanation ends in a picture. That if you push hard enough, reality will eventually present itself in a form your intuition recognizes. Feynman didn't think this was naive. He thought it was dangerous, because it trains you to expect comfort where none is promised. The problem isn't that atoms are strange. The problem is that your brain insists on asking for objects when nature is offering rules. You keep reaching for furniture when the universe is written more like grammar. Quantum mechanics works. That's the part people often rush past. It works with absurd precision. It predicts spectral lines to more decimal places than any classical theory ever could. It builds lasers, semiconductors, clocks that lose less than a second over the age of the universe. What it refuses to do is turn itself into a picture you can live inside. There is no hidden movie playing behind the equations, no secret mechanism waiting to be revealed if you just look harder, no final layer where things really behave the way you hoped all along. When you look inside an atom, you don't find a smaller world. You find that the idea of a world made of things quietly dissolves. What remains are patterns of permission and prohibition, relationships without carriers, outcomes without narratives, mathematics that does not describe what is, but what can happen if certain questions are asked. And this is the warning. If you demand that reality make intuitive sense before you accept it, you will misunderstand it, not because it is obscure, but because it is indifferent to how you prefer explanations to feel. Feynman's point was never that quantum mechanics is mysterious. It was that your intuition is provincial. It evolved to throw rocks, track prey, and avoid cliffs. It did not evolve to understand a universe where measurement creates outcomes, where structure comes from absence, and where the deepest layer of reality is not substance but constraint. The universe does not hide its workings from you. It simply does not translate them into pictures. And once you stop demanding that it do so, something strange happens. The discomfort remains, but so does the awe. Because from rules alone, from abstract permissions written into mathematics, emerges everything you recognize as solid, continuous, and real. Not because the universe explains itself to you, but because it doesn't need to.